Good morning, everyone. You're very welcome to today's webinar. My name is Dara Reynolds. I'm the marketing manager here at ComSec. I want to start by giving a big thank you for everyone to joining us today. The response to the webinar has been fantastic, and it's been a little while since we had a CheckScan Plus webinar, so I'm delighted to see some familiar names and some new ones on the attendee list. At ComSec, we're all about supporting our cybersecurity community. So if there's any topics you'd like us to cover in the future, then please get in touch by email, marketing@comsec.ie. Just some housekeeping before we start. We'll be providing you with a recording of the webinar later today, so you can share it with your teams. We'll also have a Q&A session at the end of the webinar, so this is your chance to ask the experts anything that comes to mind. You can submit your questions through the right-hand panel of the webinar screen at any time. So why are we here today? We're here to learn more about vulnerability management, to discover the true severity of vulnerabilities and to see some examples exploited in the wild. Just get this set up here. So our agenda is as follows. We'll have a quick overview of today's webinar, introduction and the vulnerability management landscape. We'll pass over to John Killalay for a quick overview of CheckScan Plus and some vulnerability scanning common questions that he has and some best practices. Then we'll pass over to Nick for exploiting the impossible, which is our main content today. Nick Blundell from AppCheck. We'll have our Q&A session, and that should take about approximately 50 minutes to cover. So just a quick introduction about our speakers today before we jump into the main content. First up, we have John Killalay, Technical Director at ComSec with over 20 years experience in IT. He has helped to secure the networks and systems of large and small companies in finance, retail, e-commerce, both in Ireland and UK. And John is leading the continued development of ComSec's technical team and is spearheading new innovations around our SOC, which is our Security Operations Centre, and our managed vulnerability scanning service, CheckScan Plus. Then I'm really pleased to have Nick Blundell back again. Nick is delivering the main content. Hi, Nick.
Hello, okay, thank you, Dara.
Good, you're there. Nick is the R&D Director at AppCheck, and his main focus is innovation in the automated detection of vulnerabilities, particularly in the increasing complex and often targeted web applications. Nick has a background in computer science research and has previously lectured in operating systems, computer networking, and distributed systems at the University of Birmingham School of Computer Science. He enjoys teaching, coding, and talking about vulnerabilities and coming up with great ideas to fix them. So looking forward to talking to Nick. So let's dive in. The vulnerability landscape. So what is it? So cybersecurity at its heart is the management of risk related to internet-connected businesses. Vulnerabilities are an important part of this because hackers, as we know, can exploit vulnerabilities to gain access to corporate networks. And today, vulnerabilities now pose probably the greatest risk to organizations and has overtaken phishing as the #1 cyber attack vector. So this highlights the importance of doing regular testing, reporting, and remediation activities. In 2021, there was 66 zero-day vulnerabilities disclosed by NIST, just over 20,000 in total. As you can see, there was a 9% increase on the year before. And earlier this year, Spider Labs forecasted that to be a 35% increase in vulnerabilities for 2022. So we can see it's not slowing down anytime soon, unfortunately, but we're well armed anyway to take it on. And it's not just web apps that have increased risk from vulnerabilities. We've also seen IT infrastructure related CVEs. Probably most of note, Microsoft, Fortinet, and VMware were severe ones published this year. And we know cyber criminals love vulnerabilities because they jump on these disclosures and find additional weaknesses, weaponize them, and exploit them in the wild. According to a recent report from Malwarebytes, the average time to exploit is within 8 days of a vendor's publication of a vulnerability. So this trend highlights the importance of regular security testing, in particular vulnerability scanning, proper patch management, and a threat-informed approach to risk management of vulnerabilities. Now, with that said, I'll pass you over to John, who's going to give us a quick overview of CheckScan Plus. Good morning, John. How are you?
Not too bad there. Morning, everyone. Thanks for joining us.
Just share your slides, John.
Yeah, share now. So I'm just going to give a quick overview of CheckScan Plus before I hand over to Nick. So what is CheckScan Plus? So it's a managed vulnerability scanning service supported by our experienced pen testers and security analysts. It uses industry-leading application and infrastructure scanning technology. We deliver verified reports from our pen testers and security analysts, and then we can also run ad hoc scans, such as for the Log4j vulnerability. So what can we test? So we can test a wide range of things: external websites, web applications, APIs, external infrastructure, such as web servers. We can also scan internal web applications, UAT and development environments, internal infrastructure, such as with servers, network devices. And we can do all of this from one central console. So I suppose some common questions around vulnerability scanning related to that. So I suppose, what is a vulnerability scan? It's a method of identifying security weaknesses and flaws in systems and the software that's running on them. How often should you scan for vulnerabilities? I suppose as regularly as you can, or as budget permits. Reporting maybe every 30 or 90 days is ideal. Statistics have shown that it only takes 8 days on average, as Dara mentioned, for an attacker to exploit a known vulnerability after it's released. So does your scanning tool provide the coverage you need? Well, different tools can scan different things. So it's about looking at what your tool can do. Does it cover applications, infrastructure? Because you need something that can kind of cover everything in your IT environment. DAST is a kind of a term mentioned quite a bit, and I suppose, how does it relate to vulnerability scanning? So DAST is a broad term that sort of describes testing of a running instance of an application, and it's tested it, probe it using real traffic and requests. And I suppose vulnerability scanning would kind of fall under that in terms of scanning those applications. I suppose, can a vulnerability scanning be used to scan complex web applications such as single page applications and APIs? Yeah, but sometimes a different method is required to do discovery. I suppose you check with your scanning tool to see if it can do those kind of applications. Dara mentioned infrastructure scanning as well earlier on. Why is that important? I suppose infrastructure vulnerabilities can still be used by attackers to compromise a system, such as missing operating system patches, weak administrative passwords. So it's important to verify and fix these quickly. I suppose, how do you process the results of a scan? So I suppose a lot of scanners can produce, a lot of output. So it's about integrating those results into your overall vulnerability management process. And they should be prioritized and allocated to system administrators, owners to resolve. So a managed scanning service such as CheckScan Plus can help with this by reviewing the findings and removing false positives. This can make it easier for IT teams to review the findings. And lastly, how does vulnerability scanning relate to pen testing? So these are two common terms used, and sometimes there's maybe a bit of confusion about which is which and which is more applicable in a certain situation. Pen testing has its advantages. An experienced tester using manual techniques will find things that a vulnerability scan may not find. But the advantage of vulnerability scanning is it is automated. It can be run frequently and on a schedule, and it's more cost effective. Pen testing can be expensive, and you may only be able to run it once or twice a year. Vulnerability scanning you can do regularly, you can do quarterly, even monthly. So you're getting more up-to-date information and finding vulnerabilities instead of waiting, for maybe 6 months before you can do a pen test. So that was all for me. It was quick. I'm going to hand back over to Dara now to introduce Nick for the rest of the webinar.
work away.
Yeah, thank you very much. Yeah, thank you for that. Thank you for the introduction, and I'm going to talk about the side that we work on now. So we develop software for scanning, automating the process of finding vulnerabilities, but we often like to talk about the technology behind it and the problems that we're trying to solve. So this is purely educational, and I thought it'd be nice to put together a load of stuff about we often talk about what vulnerabilities are, but sometimes knowing that we've got a vulnerability and knowing how to exploit it are two different things. So we might find a vulnerability, but then we've got to figure out how to exploit it. So I'm going to just try and cover that stuff and show you some of the harder exploits, stuff like that. Anyway, let's get going. So my name's Nick. I work for AppCheck. I work alongside Dara, and we basically live and breathe vulnerability research. We like to find vulnerabilities. Our background's in pen testing, computer science. We like to understand how things work and then find where the weaknesses are. We do ethical research. We publish our findings to vendors and help them to get stuff fixed. But our main bread and butter is our scanning engine that we develop. And we base it on the principles of pen testing. So the idea is that we use first principles, so we don't just blindly fire in stuff and see if something happens. We use feedback from the system that we're testing to see what happens if we inject this character. Does it get altered? Does it get filtered? How does it change it? Because if it does it this way, then it might not be vulnerable that way. But if it does it that way, then it might be vulnerable, and we might be able to bypass a filter. So that's kind of how we approach our software. We make it as much like a human as possible. But we're going to be talking about vulnerabilities today. So what's a vulnerability? How do we find vulnerabilities? Just briefly. And then we're going to look at exploiting vulnerabilities. And these talks, they're not aimed at, I don't like to miss the technical detail, but I don't like to, leave people wondering what the heck's going on. So I try and make them accessible. So we'll have technical detail in there, but it will be accessible for both technical and non-technical people. And hopefully you'll get something out of it. But let's carry on. So what's a vulnerability? There are two main kinds, design flaws and kind of broken input processing. So a design flaw is more like something where fundamentally the system, maybe how it integrates to another system, like a new system that integrates to a legacy system, it might not, the design itself of the integration of the two systems might mean that authentication isn't honored by the old system and can be bypassed and stuff because of how they integrate. This is a design flaw. Mostly what we're talking about when we're looking at vulnerabilities are ones where user input is badly processed and leads to vulnerabilities. So we call this coercion of user input, and that's what we're going to be looking at. So we can often model these kind of vulnerabilities in what we call a taint model. And a taint model is just a simple way of viewing any system that we're looking at. It doesn't matter what it is, whether it's a website or a service running on a particular port, it doesn't matter, or an app on a phone. We can model it in this taint thing. So we have this idea of a source of input that we don't trust. So this is coming from the user. So user input, we never trust it. We have a process, so we call that the source. And the source data flows through the application. And along the way, it might get manipulated, it might get filtered, it might be checked if it's an integer, if it matches a regular expression. If it doesn't, then it would be rejected. So there's some kind of middle filtering that happens with that data, which may or may not be present. Some applications might be vulnerable and they might not have any filtering in the way. So it's easy to exploit in that sense. Some might have some filtering, but the filtering might be flawed. It might be a regular expression, we can bypass it to reach the vulnerability, something like that. But there's a bit in the middle. So there's the source data, there's a middle part that filters it, and then there's the sink. And by sink, think of water flowing down a sink. The sink is the bit where there's a piece in that system where if dangerous input reaches that particular piece of code, then the attacker could do something bad. They could execute a command, they could manipulate a database directly to access or inject arbitrary data. So a sink is where the bad stuff happens. So the data flows down from the user towards a sink. And if these three conditions are met, if there's user input not correctly filtered and it reaches a sink, then that leads to a vulnerability. So all vulnerabilities can be described in that way. That's just the theory. So how do we find vulnerabilities? Well, we need to find all the places where user input goes in, because we just said that the user input is where the dangerous stuff comes in, and we'll often find in applications that parts of the applications might be being cautious about user input, but other parts of it might not even view it as user input, but actually a header in a browser request that a user doesn't usually control in their browser can be manipulated because it's part of the request. So that's part of the attack surface. and that's user input. So we look at all the stuff that can be fed into the application, and any user journeys, so particular flows. So it might be that we have to do this first. We have to click on a product in Amazon and add it to the basket and check it out, and then go to the payment and do all that flow before the vulnerable path triggers. So we need to know about any kind of flows like that, where they exist. And then, yeah, the more we see of the system, of its attack surface, and understand how to get data validly into that system, the more likely we are to find vulnerabilities. If we miss part of the attack surface, we'll never find that vulnerability, obviously. So, and then fuzzing is usually the way that we would approach a system. We don't know what the system is. We often don't make any assumptions about what the system is running. It's quite common when we often test government and council websites and stuff like that. And it might be partially implemented in PHP running on a Linux system, and then you navigate to a different page, and that's actually being proxied to a .NET application. So we don't make too many assumptions about what we're attacking. We just say, this is the attack surface, and we're going to probe it with all different techniques to try and find out what's going on. So we take each input and we try some payloads and we fuzz them. That's the gist of how it. So we're going to start by looking at remote command execution, which is so this is the worst kind of vulnerability. This means that an attacker can inject any command onto that system and run it, and it would usually lead to a full takeover of that host. So it's the worst kind of thing. Can I just check that everyone can hear me okay? Can you hear me?
Yeah, should be fine, Nick.
That's good. I didn't want to keep talking in case I'd gone on mute or something like that.
That'd be really embarrassing.
Yeah, it would, and a bit boring. But yeah, so remote command execution, let's start here. So suppose we have an image, and this is one vulnerability that I found a few times on different applications because it's a common scenario. We have an image where we can upload we have an application where we can upload an image. Let's say it's an avatar image for your user profile. Most applications let you do that. And there might be an option somewhere, either visible to the user or in the background of the request, that says the size that the image is going to be resized to, because usually the image is quite big when you have a photo, and then it resizes it to a reasonable size. And it's common to find this implemented insecurely. And we're going to look at an example of that. So there's a tool called ImageMagick, which is often used, especially on Linux systems. And it's a very convenient tool because you can take any image format and you can just run simple commands to like resize an image, like this example here. So convert input.jpg resize, and then you pass it the new dimensions, and then the file to write out to. Okay, so that's how it resizes an image. So this is a classic example because supposing that the user is able to specify the size that it gets resized to, but if this is passed directly into the constructed command, that ImageMagick command on the system that we're attacking, without any kind of sanitization to make sure that it's numeric and it looks like a dimension, nothing else, then this can lead to remote command execution. And this is an example of how. This is a bit of PHP code because you don't need to know PHP, but most people that have done coding are familiar with it. But all this bit of code is doing is highlighting that at some point in this system, the request which comes from the user, the form when they upload the image, has a size field in it, and that gets stored in the size variable in the system. So when it's processing our request, and then to convert the image, it uses this function shell exec, which runs the convert command to resize it to the value that's passed in from the user. And because there's no sanitization here, this means that anything can be injected into this command line. And anywhere that you touch a command in a system, if the user is able to touch part of that command, they can probably get remote command execution. When it's uploaded the file, it prints a message to say uploaded file has been resized. And also the developers will see this is useful. I've left in this thing where usually when that convert function runs, that command it runs, when it converts the file and there's no problems, it doesn't say anything, there's no error, there's no output. But so that the developers can debug it, they return the output of the command, which you'll get output if you get an error. And also in our case, we'll find that we can get output of the command that we want to inject. So an attacker might manipulate the input to run in a command and then view the output. So how do they do that? Well, what they do is, for the size of the image, rather than having like 100 times 100 as a dimension, they put this backtick cat etc password, which is a file, backtick, in place of the image size, and the command that gets constructed by the system then becomes convert uploaded image resize, and then this part of the attack is injected. And backticks in common Linux shells like Bash and Shell then the backticks set off a new command in place of the existing command and output the output of that command. So it's a convenient way for an attacker just to completely run a different command embedded inside the other command that the application was using to resize the image. So the outcome of this is that the page that comes back to the user now, or the attacker when they've injected that, dumps out the contents of the file that they just ran. Cat, so cat is a command, means cat, it means output, like concat as well for joining files. It just means list the output of that file. And this is the user's file on Linux, so it's dumped it out. So at this point, the attacker knows we've got remote command execution, so that's pretty bad. It's game over then, they can do whatever they want. But what would an attacker usually do? Well, they've confirmed the vulnerability because they dumped the output of a sensitive file on the system. But now what they would do is open a remote shell onto the box. So this means that it makes it easy for them to run any command they want without having to keep posting their file upload, you know, and doing all that stuff. So they would open a remote shell, which I'll show you in a minute, and then they'd continue with post exploitation, which is like, do they need to elevate privileges to root user, to the super user? Can they, what other networks can they access if they've managed to get into an internal network somehow that's proxied maybe? And then they can internal access networks and start scanning deeper into the system. So pivot into the system, as we say. So a common way to fire up a remote shell when we've just found remote command execution on Linux systems is to use, and there are many ways to do this, but netcat is the kind of traditional way of doing it. So netcat is just a simple command, so it's NC. And what it does is it allows an attacker just to run this command. So if they inject this in place of size, now what this one does is it takes the shell, which is bin bash, so the command shell, and it binds it onto a port 5555, a remote port on that machine. And it basically sets up the attacked machine, the victim machine, to open up a shell on a random port, so 555 for the attacker to connect into. And it's just as though they've logged into that machine. They can run any command they want on it. So when they do that, they've opened up the port, they've injected their payload to open up the port, and then they just use something like telnet, which is a simple command that lets you open a connection, and you can start typing commands in on the attack machine to exploit it. So you can see some commands there about the network and you know which user you are. So that's pretty bad. That's why I said it's bad, because it gives them access to your machine, which we don't want. Now, that was a vanilla vulnerability, so there wasn't anything too complex about exploiting that one. We found a vulnerability, we just injected a straight command, we got output from that command, and then we were able to inject a command that opened a shell. We connect to the shell, and then we've pretty much taken over that machine. So let's have a look. Supposing that machine was not directly reachable, so it wasn't on the public internet, for example. So if it wasn't on the public internet, what it might mean is that the attacker might be able to inject a command onto that system, because often there might be a public facing proxy or something like that, but it routes through to another system. And then when they open their shell on that system, on that port 5555, they might find that they've actually opened that shell on some internal host somewhere that they can't see from the outside, so they won't be able to connect to it. Similarly, it might be on a public facing host, but it might block incoming connections to arbitrary ports, like our attacker shell port. It might open ports like 80 and 443, those common ports, but it might block any ports to anything else. So again, the attacker won't be able to connect in. So what can the attacker do in that case? Well, they can do a thing that we call the reverse shell. So which is what it says really. So what it means is the attacker, they think they found a vulnerability on that system, but they can't connect into it to confirm it. So what they want to do is they say, well, most systems, if you can't connect into an internal system on an internal network, it's probably able to connect back out to the outside world. So they do a reverse shell. So the way it works is the attacker opens up a listening port on their own public facing server, so like attacker.com. So they open this port. So they're just listening for an incoming connection on that port. And then the attacker injects this here. So instead of a bind shell, we call this a reverse shell. And what this does, similar to before, it runs the shell, so the command shell that they can run commands on, using netcat, but it makes a connection out to the attacker's machine. So it's not listening for a connection to come in from the attacker, it's making a connection back out to the attacker's machine, their public machine. So the internal host will send an open request to the attacker's host, and then the attacker will be waiting, looking at their console, and they'll see the connection come in, and then it doesn't matter whether they're connected out or somebody connected in. They've got a shell again. It's the same thing. It's opened up that connection. So they trigger an outbound connection, which of course gets them into the internal network then. So that's good. That's a reverse shell. But supposing that the vulnerability discloses no command output. Okay, so if we look at that example, the reason why the attacker was able to find the vulnerability was because they ran that function, that command cat, etc. password, which dumps the user's file. And because when that shell ran to convert the image, the developers left in some code, some debug code that printed the output of the command, which usually there will be no output unless there was an error of the command. And in this case, the attacker forces some output by dumping the contents of a file. Then because the attackers put this in, not the attackers, because the developers put this in, it gave the attacker a gift to see the output from the vulnerability, which is the easiest way to confirm vulnerability if we see actual output coming out from the vulnerability. It might be an error message, it might be a change in the page that we can look at, but this one is a real gift. So supposing the developers change that now, they think maybe it's not a good idea to have that debug code in there. So they leave everything else the same, apart from the fact that they no longer echo the output of the command that runs, but they've not actually fixed the vulnerability. You can see here, it's the same code as before. So when the attacker tries that command to dump the output of the file, the vulnerability is still there and it will run that command, but they'll see no evidence of the output of that in the actual application after they've uploaded the file, because all they get now is this message that says uploaded image has been resized. That's all they see. Even if there's an error in the command, it will still print that message in this case. So that's not good. So how are they going to do it then? How's the attacker going to find it? Yeah, so it's just that there's no clue in the response now. So we talk about this as a blind injection scenario. So there is a vulnerability there, but we don't see any direct output from that vulnerability. So how's the attacker going to find it? Often in these cases, we can make use of a side channel. Now, an obvious side channel, one that's commonly used for all kinds of injections, blind injections, SQL injections, is to try and inject a sleep command. Okay, so the idea is that if we manage to inject a sleep command and it is vulnerable, so it is running any command that we send it, then we might cause a proportional delay in the response time that comes back to us that we can measure. So even though we don't see any output from the vulnerability, we can see that we cause the response to be delayed by 5 seconds, 10 seconds, 15 seconds. It might be double of what we input, for example, because it might run that input twice. We don't know, but it will be a proportional change. And when we inject a high delay, we'll get a high latency on the response, and a low delay, we'll get a low response. And after a few of those attempts, we can correlate it and say, yeah, we found a vulnerability. So that's how we find blind vulnerabilities. But what if the image is resized in a background task? What this means, and it's quite common, so supposing the developers decide that when the user uploads an image for their profile, that they shouldn't have to wait for that image to be processed, especially if it's more processing is involved. Like maybe there could be some filtering to check if it's an indecent photo or something like that. There could be all kinds of stuff that happens. It could get uploaded to cloud file storage. So there could be a few, maybe seconds, could be or even longer delay in processing that image. And they don't want the users to have to wait until it returns the page and says your file has been uploaded. So in this case, they background the task. They make that happen in the background. So what does that look like? Yeah, it just looks like this. When they upload the file, the image file, the application now just responds immediately. And now it says your image is being processed. And the way it does this is it takes the input on the size of the image, and then it says run in the background, resize user image, and it passes the thing in. Now, this is the background function that gets called in the background. And it's exactly the same. It's still vulnerable. It passes the size directly into the command so that the command can be manipulated by a user. But the thing is now, and this might run at any time in the background. It might get queued to run, in the nighttime, for example, if there's a lot of processing on that image. But it's still as vulnerable as ever. But what it means now is that if the attacker tries what they did before, so it's blind because we don't get any output from it, but also if the attacker injects delays like they did before, so sleep 5, sleep 10, those sleeps will affect the command that runs. They will cause it to be delayed, but because the job runs in the background and the response comes back to us immediately to say the file's being processed, it has no relation to the latency of the response that the user sees when they've uploaded a file. Okay, so they've lost that side channel basically now. They can't use the sleep to determine if it's vulnerable or not. I hope that makes sense. So basically, you've made it. You've taken before the processing was in line with the request comes into the application from the user with the file, and the file gets processed, and then a response comes back. They're in line. So if the file command takes longer, the response will take longer to come back. But now they're not in line. We call it asynchronous. So the job runs in the background and the response comes back immediately, however long that job takes, which is why the developers did it, because they didn't want the user to wait. So the attackers lost that ability now to detect that vulnerability. So how can they do it now? A typical approach for an attacker to identify and exploit this vulnerability is to find a way to use the command to exfiltrate some data directly to the attacker server. So a common example here is to use a command like curl, which is often a curl, which is often installed on machines for downloading files and stuff. And they can, if they inject this command, then what happens is it says take a file off the server that we're attacking and upload it to attacker.com, so the attacker's web server. So the attacker just has a web server listening like that. Now the attacker, by doing this, the attacker no longer cares if their payload triggers immediately or later or as a background task, because whenever that injected command triggers as part of that image resize job, it will run this command and it will just take a file off the server and upload it straight to the attacker's machine. So now they don't care. They'll just be sitting by or waiting for a notification on their hacking server, and they'll get a notification saying, "Oh, a file's just been uploaded. It's got the user file from that machine, or or the SSH keys have just been grabbed or something like that." So they can exploit it, even if it's a background task, if it's asynchronous. So that's good. What if outgoing connections are blocked? So supposing that the host that's got the vulnerability, so let's now suppose it's running it as a background job on some back office server that does all the processing of images, and it's vulnerable as ever, but the infrastructure guys have been looking at it and thinking, actually, if we get hacked, somebody might try and make an outgoing connection and get a reverse shell or exfiltrate data. So let's block any outgoing connections from our internal network on this particular host. So it's quite common to have that thing on very sensitive systems, especially like card processing systems, payment cards and stuff like that. So they block outgoing connections. So what happens now? So what happens is when the attacker tries that exfiltration, so they use curl, they say, we don't know when the command's going to run because it runs in the background, but when the command runs, it's going to take a file and upload it to the attacker's server. But now what happens is when the server tries to connect to attacker.com, it goes, that's an external, that's on an external host. That's outside of this this secure network, so we're not going to connect to it, and the firewall would block it. So the file would never get uploaded, and the attacker would never know that it's vulnerable, so they didn't know it, but it's still as vulnerable as ever. So let's have a look. Now it turns out that even the most locked down networks that block outgoing connections still allow DNS resolution, so domain names to be looked up. So a domain name, most people will be aware, but if you're not, it's the bit that when we have attacker.com, when we want to connect to a server by a name, servers all have an IP address, and the IP address is numeric. And to connect to that machine by a name, we do like a lookup called DNS, and we look up the name and it gives us an IP address, and then we connect to that IP address to do something. So even though the internal system might not allow outgoing connections, it might allow DNS resolution to external DNS names, because it's quite inconvenient to lock down DNS on a system so that you can't even look up names to find out if they're internal or external, for example. So let's have a look now what happens. So if we take that last attack example and assume that outgoing connections are blocked from the host. So now when the attacker injects this thing, curl, can you see my mouse pointer just to check? So when we attack Perl,
Yes, Nick, all good.
that's good. Yes, you know where I'm pointing. Good. So when they run this command now, so it's going to run in the background. It's going to try and exfiltrate that file to the attacker.com. But it's very likely that what actually happens on this system that's blocked by a firewall for making outgoing connections is that the attacker.com host name was actually DNS resolved. So it was resolved from the name to its address. Okay. And then it tried to connect to that address, and then the firewall said, hang on, that's an external address. I'm not connecting to anything external. Sorry, mate. So it blocks that exfiltration of the file. Now, but the fact is that it did resolve the address. It means that it communicated directly or indirectly through an internal DNS server that then looked up an external DNS address. It communicated with an external DNS server outside of that internal private network to look up the name to then say, we're going to block connecting to that thing because it's external, but it did look it up. So the attacker now thinks, I wonder if they're blocking outgoing connections, but I think it's still vulnerable, or I think there's vulnerability here. So the attacker then decides that on their attacker.com domain name, they decide to handle all DNS requests. So usually if you register a domain, if you're like a private owner of a domain or something like that, you might let the registrar, the company that deals with the registrar, they might handle all DNS lookups on that host, and you just say, I want to point you to my website. But you can take over control of that if you want to do the DNS resolution yourself, because it's your domain. So that's part of owning a domain. So supposing the attacker takes over control of their own domain name, so they can watch all the DNS resolutions and route them to their own DNS server. So now what the attacker can do is they can inject a command like this instead onto that host. So we're injecting into a host that blocks all outgoing connections, but the attacker says, I'm going to inject this command, which is the host command, and the host command is just a simple command that does a DNS resolution of a host. It doesn't even try and connect to it. It just looks up the IP address for this particular host name. And the attacker uses a random token on the start for their host name, because the attacker knows that if the internal system that blocks outgoing connections is still resolving external DNS addresses, then it will look up this host name to try and turn it into an IP address. And at that stage, the attacker can just listen out on their DNS server to see if this name ever gets requested, and they know by this random token that they injected that into this particular file upload system somewhere. So they know that they've triggered that host lookup on the internal network that can't make any outgoing connections, but they've been able to trigger that command on it. So they know they've got command execution, even though it's quite locked down. So they know they found a high severity vulnerability then, which is good. But without being able to make any outgoing connections from that host, how can they easily exploit it? I mean, how can they actually exploit that vulnerability? So they can get it to do DNS lookups, but how do they, break into the machine? What can they do? So let's have a look. So it turns out that they can use DNS resolution itself as a kind of channel to exfiltrate data. We just saw that when we detected that vulnerability, we put a random token in, and we saw the system, the internal system that's vulnerable, resolve that random host name because we saw it come back to our attacker-controlled DNS server. So we got a random token in. The random token we can view as data. We could use data in place of the random token. So it could resolve a token that actually is made up of data coming out from the machine. So this is how it works. So we have to understand a bit about how DNS works. So a valid DNS name has sections, so it has like something dot something dot something, and each section can be less than or equal to 63 characters long. They're alphanumeric, and there's a hyphen as well in there, but they're basically alphanumeric characters, and you've got 63 of them. And it actually turns out that in 63 alphanumeric characters, if you look at the permutations of that, you can encode quite a lot of data. But what you do is because you've got that restriction on how much you can exfiltrate at a time, you chunk up the output of some data that you want to exfiltrate. You encode it as a part of a DNS name, so make sure that it's alphanumeric. So it might be binary data, but we can use things like base 64 or base 32 in this case, which turns binary data that could be any value into data that fits in an alphanumeric character set. We can then decode it when we want to find out what that original data was. So this is what they do. I'll show you an example. You don't need to worry exactly how this works. I'm just explaining the principle. This is a little bash script that we can inject in place of the size for that vulnerable upload. We can inject this thing, and what it does is it it runs a set of commands that the attacker wants to see the output of. So they want to find out who the user is and look at the network configuration. So it runs these commands, and then it splits up the output that comes out of those commands. It encodes it in base 32. Base 32 is just a convenient way of getting it down to alphanumeric characters so that we can encode it as part of the host name in the DNS lookup. And then for each of those chunks, we run the host command, which we did before with a random token, but now we're doing it with the encoded chunk data from the output of the commands that we want to exfiltrate, and it just joins it onto attacker.com, and it just tricks the system that we're attacking to resolve all of these strange host names. And we'll see when the attacker's watching their DNS server, they'll see all these requests come in here. We also had an index at the start so we can sort the data so we know which was the first chunk, which was the second chunk, because they can get mixed up when you do DNS lookups, or they can get duplicated even. So these are the host names that get looked up by the machine. So it's not connecting out to the outside world. It's just resolving names on an external DNS server, but we're encoding the data that we want to exfiltrate inside those names. And so all this strange looking stuff is the base 32 encoded output of the commands we ran. And all we need to do now is combine all that together, these together. So take off the index, combine these chunks together, which are base 32, and then decode them, base 32. And we'll see the output of the commands that we injected into the victim machine. So we've managed to exploit it, get sensitive data out. We might get SSH keys, and then we can just log in with SSH or any other secrets. And we've done all of that without having external connections. And it was also done in a backgrounded tasks. There was no direct output. It was blind. So it shows how attackers can how they can exploit stuff in a really hostile kind of situation. And it turns out that DNS is very useful for detecting and exploiting vulnerabilities, something that we often use in the scanner as a way to verify or confirm other results. If you can trick a system to resolve DNS address, and most systems can, even if they're quite locked down, then we can use that to detect vulnerabilities. So I hope that made sense. But still getting started. Well, when I say we're getting started, this talk can go on for a little bit longer, and we usually make the slides available. So there's some more stuff. I won't cover all of it now in this session, but I'll whet your appetite a bit.
Another 5 or 10 minutes there, Nick.
Yeah. So I'm gonna get started on this, and you can dig more into it if you're interested. But we're going to look at insecure object serialization, which relates to the other vulnerability, but it's like a level up. So this is a kind of vulnerability that leads to remote command execution. And you would have often heard stories about Java serialization vulnerabilities. You know, we always hear them every year. There's a few big ones. So let's have a look about that, because they all relate to serialization usually. So I'm going to really quickly go over this. A few years ago, someone decided that, or a few people decided, rather than having programs defined as a set of functions that call each other, it's good to break programs into what we call objects and classes. It means rather than having functions, just functions, and then the data works on functions, you have an object. And an object, thinking about an example here, for those who haven't done programming or object-oriented programming, all it is that we encapsulate data, so like name, date of birth, and functions that relate to that data inside an object. It's an easy way to encapsulate the code so that if somebody changes the person class, for example, in this case, it doesn't affect much of the wider system in a way that it would have done without object-oriented programming. So we can define things as separate entities. So then once we've defined this person having a name and a date of birth field, we can add an age function, which when we call age, it just calculates the age from the date of birth and today. And we can create instances of that class. So Bert and Ernie are people, and they have names and dates of birth. And then we can do things like if Bert.age is greater than Ernie.age, print that out. That's the gist of what object-oriented programming is. Okay, so objects are quite useful for structuring code. And naturally, some people thought, well, it'd be quite nice if we're coding in objects that we can store those objects without worrying how it happens, and also send those objects over the network. So if I have a person object, we might want to send that person, so Bert or Ernie, over the network to another system that does some stuff for that user, maybe updates their account or something like that. So people thought that would be a good idea, and they thought it would be good if they didn't have to worry about how it happened. And this is generally known as object serialization, so sending objects over the network. And it allows code to be written as though the objects are being sent and received to remote systems. Sometimes the developers don't even need to care that it's a network that they're using. But in fact, the way it works is that obviously when it gets sent over the network, some part of the framework takes the object, like a person, it squashes it down into a stream of bytes, we call that serializing it, and then it transmits it over the network. And then when it gets received on the other side, it takes that stream of bytes and reassembles them into an object that has all the same properties as the original one. So it looks as though the system just received an object. Certain objects can't be serialized. So if you open a file on your system and a file is represented by an object, that's an open file on your system that you're reading. You can't send that object to another server because it's got a local resource, if that makes sense. But for things like data objects about people and stuff like that, we can send them over. So what can go wrong? This is what we're interested in. So the thing that can go wrong is that since by design, I'm focusing on Java here, but this can apply to all languages that do serialization. Since by design objects encapsulate data and methods, there's a possibility that some of those methods might be triggered during deserialization. So when we think of sending an object about a person over the network to the other side, we might think, well, when it gets to the other side, it just loads that object and it has all the same values and fields. But sometimes classes customize the deserialization, the turning back into an object part to do something, maybe to optimize something or something like that. And it can lead to methods being called automatically when it gets deserialized, and sometimes bad methods can be called. So the hard bit with this, and it's probably why we see it all the time, is because you can have an object can contain another object. So you can have a person object and they might have tasks, and a task could be, they might have a list of tasks that go inside the person object, or vice versa. You might have a team object and that has a person there are lots of people in the team, so you put them inside it. But basically objects can be deeply nested. They can have lots of other objects inside them. And even though an object might look like it's safe to send over the network, internally it might use some other complex objects that are not safe. They can do too many things. I'll explain that in a minute. But one example is sometimes you might think, well, a string object just describes a sequence of characters, so that doesn't sound too bad. But some frameworks, some languages and the way they process types, simple types, can sometimes lead to traversing from a simple type all the way to a command execution type. It's a part of what we call reflection in languages, where languages are able to interrogate their own types and stuff. Java does that stuff, and often scripting languages like Python and Ruby and all that stuff does it. So that's reflection. So in Java, so I showed an example of a class before. In Java, we would create a serializable class like this. So we don't worry about all the keywords here. All this is doing is saying, I want to define something called a message. And my message is serializable, so it has to implement this in Java to make it so we can send it over the network. So this is saying message is a type of serializable object. That's all we need to know about that. And inside it's got a piece of data called text, which is just a string. And this is called a constructor. We don't need to worry about this. But when we build a message, we pass a string in of the message we want to send, and it stores it inside the object. And we add a function called getText, which prints the text out the screen. We don't really need that because it's just returns the attribute, but it's just demonstrating that we can access the data with functions in a class. So let's have a look at how we do it. So supposing that there's a system that has these messages and it sends them from the client to the server using object serialization. And this shows you how easy it is to work. We don't need to worry about networking here. All we do is we create a message called a new message called my message, and we pass in the string hello. And all we do is in Java, we create this thing called an output stream, an object output stream. We wrap one in the other. You don't need to worry too much about that, but it creates this transport layer that we can say, take my message. So it connects to another machine, and write the object onto that connection. So the developer doesn't need to care how that happens. They just say, I want to send this object to that server. Right, so that's the sending side. And then at the other side of the connection, the server is reading off the objects that the client sends to it. It might be a chat application or something like that, or some sort of API for doing stuff. And this is a reverse. So what happens here is that the server they've got an input stream, an object input stream, and this is where they're listening for incoming data coming from clients. It might be one client or multiple clients. And the way it reads them is the opposite of write object. So it calls on the stream, it calls read object, and it's expecting a message object. That's why that's there. And then this creates the message object as though it was created locally, but it's actually been read over the network. So this is where it deserializes it. And then it says receive the message. Incoming is the message object, and it prints out that get text function, which just prints the message. So it'll say receive message hello. That's all it does. So this is quite common way that these applications work and send objects. Now the bad guy doesn't care too much for your message class, but they did realize when they saw your code, or they played around a bit with the code, that as it's written, it will actually deserialize any object that gets sent to it. So although it's expecting message objects, and here this is called a cast, it tries to cast whatever it comes in as an object, and it will fail if it's not an object, but it still reads the object and deserializes the object, whatever it is. It will fail here if it's not a message to cast it, but by that stage, it would have already deserialized it, and it would have already done the dodgy part that the attacker's interested in doing. So, just go over this really quickly. You can always ask questions and you can get in touch with us if you've got any more questions about this, or get the slides and look in detail at it. But what the attacker is doing now, they recognize there's a vulnerability because they know that they can deserialize any object. Now, this is why I said it's hard. This is a hard thing to exploit. What they want to do is try and trick your application into deserializing a certain object type that will give the attacker arbitrary code execution on your system. Okay. Message won't do that. Message just sends a message and prints a message on the screen. But the attacker, when they see a vulnerability like this, you've seen the Java examples over the years, when they realize there's something like this, they'll go to great lengths to figure out exactly how to exploit it, and it can be quite difficult to do it. I'll just give you an insight into that. So the attacker has to work out, so they have to say, we need to find a class or a combination, we call them a chain of classes, or a gadget chain, a strange combination of classes that exist on the system we're attacking. So they might be in libraries that are imported by the application, that they don't even use, the application might not even use those libraries, but they're present there. So the attacker's got to find a combination of all different classes that exist on the server, that if they put them together in a certain way, when they deserialize, they will automatically cause code to run on the system. So this is called a gadget chain. And this is how they exploit deserialization. So the way it works is that though most objects deserialize in the normal boring way, so they just create data like the message class, some objects modify the deserialization process. And in Java, they define a function called read object, which means when it comes to deserialize that particular class, the Java framework that deserializes objects, it says to the class, do you have your own custom deserialization function? If they don't have it, then it does it in the normal boring way. If they do, then it passes over control to that object to say, you deserialize yourself then. And it's here where dangerous stuff can happen. So this often involves methods being called during deserialization. Okay, so.
Right, Nick, I think we'll have to wrap it up there. It's 5 to 12. So thanks very much, Nick. Always insightful. We will have we'll have a couple of questions here before we wrap up, and as you said, Nick, people can contact us if they want any more further information on that. So let's just 1 second here now. So we'll take a look at the Q&As. We'll give Nick a break for a second. John, one came in there by email. What is better, automated or manual testing? If you'd like to take that.
Yeah, sure. I suppose ideally you would do both, because manual testing will find things that automated testing won't. So if you look at a pen test, for example, it's a combination of both. So you're doing some automated scanning, then you're doing manual verification and exploring the application, and then you'll find vulnerabilities. But I guess, as I mentioned earlier, you can't do that every week, every month. So you kind of utilize automated scanning as well by using vulnerability scanner. You schedule a scan every month, finds things, and then you kind of find things quicker than pen testing. So ideally do both, but kind of it's not always cost effective to do kind of pen testing every week or every month.
Of course. So it's more of an annual thing. So it's kind of like a belt and braces approach to it. Nick, I'll bring you back in. Interested to hear your opinion on this. What are the reasons for the increasing numbers of vulnerabilities? With innovations in technology, are we better protected as well, or is it just that hackers are being, super innovative themselves and bypassing, some of the fixes? Or what's your opinion on this?
Yeah, I think it's a difficult one to answer, other than to say that there are always take anything. You know, often we talk about lock picking as an example. Somebody creates a new lock. As soon as somebody creates a new lock, somebody's looking to find flaws in that thing, either for a hobby, from a hobby point of view, or because they you know, they're a serious criminal, and and that's going to stop them profiting from their work. Yeah, the number of vulnerabilities, I think it's just it's healthy. I think it's healthy to take the approach that there will always be flaws in systems, especially anything complex. You know, all systems, the more complex, the more likely there are to be flaws there, or the greater number of flaws. And some of those will be, you know, vulnerabilities, exploitable. Others might be bugs that might just be nuisance, but not exploitable, not vulnerabilities, not security. So we start with that assumption and just, you know, just, I mean, things are, there are a lot more, you know, there are bug bounty programs, there are a lot more people getting involved in security research on the good and the bad side, which is probably leading to more stuff being detected. There are companies that sell elaborate vulnerabilities, you know, for sort of you know, high value to anyone that wants to exploit, you know, the latest iPhone and stuff like that. There's a lot. Yeah, I think it's just one of those things. We've just got to accept it, that any system, we can keep educating developers and designing systems that are more, you know, there are improvements in systems that can mitigate vulnerabilities, and frameworks are more aware of, there are frameworks that are more aware of cross-site scripting that should, if used properly, eliminate cross-site scripting completely. And that's because there's been awareness built up over time of, you know, the devastation of these vulnerabilities. So there are good things, but there's always going to be vulnerabilities, and it's just about staying on top of them. And yeah, definitely, like you were talking about scanning versus pen testing before. You know, you want to get rid of be aware, most aware of the low level stuff first. You know, anything low level that you can scan for quickly, mitigate or fix those ones, and then it's the more difficult, the more research heavy vulnerabilities that are going to take, they're going to be, they could be targeted, but it's going to take the attacker more effort to do that. So it's just about focusing your effort on, you know, you don't want the low level stuff, and then once you've got that under control, you can focus on, you know, is our software coding practice good?
More strategic stuff.
Yeah, so
Great,
difficult
Nick.
question, that one, but yeah.
Yeah, no, I just thought I'd throw a spanner in the works there. Sorry,
Yeah.
sorry about that. But yeah, look,
it's good.
Thanks very much. Yeah, no, this is all about it being an open forum. So just to wrap up, we've got some further resources for you to avail of today. Our partners AppCheck and ourselves, we're offering a complimentary scan on one IP address, which is a useful resource to take advantage of. You can also get in touch with us for a demonstration on our CheckScan Plus dashboard. We can show you what that's all about. The AppCheck blog is a phenomenal resource for security vulnerabilities. Nearly weekly, they have a new blog up on some new part of or some new vulnerability that's been identified, and our own CheckScan Plus website, ComSec, of course, comsec.ie, our blog as well. You get a different flavor of cybersecurity topics there, and of course on our social media as well. So thanks very much to our speakers today, John and Nick, and we hope to see you on the next webinar very soon. Thank you and goodbye.
Thank you very much.
Thank you. Bye.